Today we will start with, again, plane waves, but in the oblique incidence. Last time we had covered part of it. Plane waves. Oblique incidence. We will talk about what happens if a plane wave is no longer normally incident on a surface but comes at an oblique angle, and what happens if this is a rigid surface or it's a pressure release boundary, or if it is a different type of fluid. That becomes very interesting, and it requires attention as to under what circumstances sound will go to the other medium or not. So if we write the wave equation in an arbitrary direction, pressure in arbitrary direction, can be written as now, what is important here, once again, the time and the radial frequency and the wave number and the distance to the point from some origin, okay? And what we need to realize here is that the wave number is it's a vector quantity, and it's constant. Now, this is in some arbitrary coordinates, but in Cartesian coordinates, of course, and the vectors I, J, and K are unit vectors. When we use these, then in Cartesian coordinates, the pressure expression becomes okay, let me explain what they are. A couple of things. Let me have your attention for a second. One is this amplitude, the sign tilde, okay, indicates that this is a complex quantity, or it can be. Okay, it can be a complex quantity. Later on, we'll drop that because it's understood that it is a complex quantity. Secondly, once again, it depends on the frequency, okay? And this is a convention that we use, okay? We choose to use omega with a minus sign, I omega t. One can also use I omega t. There's nothing wrong. But when you do that, you need to make sure that the signs of the spatial variables are different. So for our purposes, we will always use e to the minus I omega t. That's all it is. It's a phase difference, but nothing more than that. Okay? So once again, you can use this, but then you have to be careful with the signs of these. Now, what does this say? What is exponential to the I k sub xx? What does that indicate? It indicates a harmonic wave propagating in the x component. But actually, it is the x component of the wave with the wave number in the x direction. Okay? Now, what we want to do is take this and substitute it in the wave equation. Okay, if we take the wave equation, oops. Okay. Laplacian is del square del x square okay. Now if we substitute the pressure expression in the wave equation, okay. We know what this is, double derivative with respect to space, and that will give us on this side minus kx squared and on this side we have omega squared or c squared times. Okay, do you follow this? Pretty much. If you take just one of these, let me quickly make a note here. Del over del x of e to the I kxx is certainly just this. And if you take a second derivative of that, and that will be minus kx squared times itself. That's where it's coming from, okay, yeah. Now, since these are the same, a times the exponentials, then what we must have is a condition called okay? And omega over c is often called k, the wave number. With the components in the x, y, and z directions. So the magnitude of the wave number remember now we had wave as a vector here, okay? So the magnitude is we can also express it as a ratio of the units, cosine units. Kx is, let's say, cosine alpha. Ky is k times cosine beta, and kz is k times cosine gamma. I think I used the gamma, yeah. And then what we would have here is okay. So that's pretty much what we would have in terms of directional cosines, wave number expression. Any questions on this? Okay, you're writing fast and furiously. Any questions? So very briefly, we started with an arbitrary direction, pressure wave equation in an arbitrary direction, and we expressed it in Cartesian coordinates, the wave numbers, and when you substitute it, you have a relationship here. Now, this is going to be this. These are the same things, okay? Very important, as you'll see in a moment, okay? And I will come back to this and point it out to you. Now, let's see what happens when we intersect with rigid boundary. Okay, let's say we have a rigid plane surface, not curved, it's plane. An incident pressure wave is making an angle, incident angle, theta I, and it reflects at an angle theta R. See if you can write these expressions quickly. Can you just exercise just for a second? See if you can write the expressions for incident pressure and reflected pressure. You use an amplitude, capital Pi and R. And what would be the dependence on time and space? See if you can write it. This should become a second nature to you. Should be easy, right? Plane wave that's going in number one, you have to identify the x and say z. Is that what I have done? Yes. See what you can do. Okay. Let me go step by step now about just thinking through rather than just writing. First of all, we have an amplitude, okay? Second, we have a frequency dependence. We always have that. So far, so good. You just have to write these down. Now, direction in space. What do we have? Let's take a look at this. It's going in this direction. So, what does it do? It has a positive x and a positive z component. What is x? As you can see, x will be in the cosine. So what you do write is positive I k cosine theta I times x. See, this is the wave number in the x direction. This would, in fact, be k sub x that we would normally write it. See, no different than here. Kx. This is my 2 minuses make it, okay? Kx is x cosine theta I. Well, what about the z direction? It has a component in the z direction, and that's also in the positive direction. So you have I, what is it now? Sine theta I in the z direction. And this is, of course, ky, kz. Now let's go back to, that was supposed to be pi here. I wrote in the wrong place. Okay. Let's go and look at the reflected wave now. Okay, the reflected wave, let me write it down here, also has the harmonic time dependence. Okay, can you now tell me what the spatial dependences are? Okay, yes?
E to the power minus I times k cosine r.
Cosine theta r. X, because it's coming in this direction, plus
I k sine theta r z.
Exactly. Okay, that's the expression. Once you start thinking and doing these, it seems to be a lot easier. Now, what we have is a sound field in front of this wall, okay? In front of this rigid wall. And what is the total sound field? Sound field. What is the total sound pressure here? Exactly. So we have really x, z, and t. Okay? The pressure at any position is a sum of incident and reflected pressures. Well, we can add these, but we have some unknowns. The primary unknown is the relationship between the angles. What is a boundary condition that we can use to determine that? For a rigid surface, what do we have? Exactly, because rigid surface doesn't move. You have to remember these. Rigid surface does not move. And so the velocity is 0. Where is it 0? It's 0 at, sorry? At x equal to 0, normal to the surface. So u sub z must be 0. Very good. Okay, let me clean this part. How do you find the velocity? I'm sorry, say again? It is u sub x. I was just testing you. No, thank you. It is u sub x. it's a normal to the surface, which would be in the extraction. Very good, thank you. I made a mistake. Okay, and how do we find that velocity there? The relationship, if you remember, is always right? And the time dependence being I omega, so you have here, this is an easy way to always drive these equations. And what do we have here when you take the derivative of, in this case, let's make it pi with respect to x. Okay, and k being omega over c, so you have ux as cosine theta I divided by rho c times pi. Similarly, you can find, sorry, this is ux at the incident direction. Similarly, you can find uxr as cosine theta r rho c pr. Except that there will be a negative here. Now, when we apply the boundary condition then, okay, this must be 0. Okay. So particle velocity, pressure, particle velocity component, pressure, that must be equal to 0.
Aren't they supposed to be signed for that component?
Oh yes, 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 yes. What am I? Sorry. These, they are in the z direction, yes. Yes. This y. X reaction, no. With respect to x, it's always cosine. Yeah. Okay. Okay. The only thing we have to do here is to satisfy that equality, it has to be evaluated on the surface. Okay? So x must be 0. When you do that, what do we know about these? You realize that whenever you have an equation like this, okay, for it to be satisfied under all conditions, the exponents must be the same. Okay? And from there, we now say sine theta I must be equal to sine theta R. So the incidence and reflection angles are the same. Now we know that incidence and reflection angles are the same. We go back and substitute for the total sound pressure. Well, let me see. There's some other things here. If they are the same, rho c are the same, then cosine theta, cosine r are the same, then that must also make the amplitudes the same. Okay? So what we have is an expression pi this a little bit differently. Cosine theta I right. Okay. These two components we can combine to write as 2 times cosine kx cosine theta I. You know the relationship there. Okay, so let me just clarify that. Okay. Have you written this last part? Okay. I will just rewrite it up here. This is the sound field in front of a rigid wall, in front of this wall. Okay? And you write it and let's talk about it just for a moment, see what that means. Okay, what do we see here? What did we do, number one? We took two components. What does this represent, this portion? What is this portion? What does this mean? Go ahead.
Propagating wave in the X direction.
Exactly. It's a propagating wave in the positive extraction, wave component in the Z direction. This is propagating in the negative extraction. This is in the Z. And when we combine them, we have what now? This is wave component that's going towards the wall and coming back. And together, they form what's called a standing wave. And I'll try to explain what that means, a standing wave. And this is the progressive wave. It's really just the spatial part, not the time part. Okay? So while we have a standing wave here, it keeps on moving parallel to the z-axis. Physically, what does this mean? Do you know? What it means is, if you have this surface, if there's a progressive wave that's going on, and you have a microphone here, or actually anywhere, and let's say you have a progressive wave only in that direction, and on the oscilloscope, what you'll see in time, if it's a sinusoidal wave, sin omega t, you will just see the pressure at that amplitude, just one amplitude. That's all it is. Now, if on the other hand you have a standing wave, what that means is you will have places where this microphone measurement will have a minimum, and other places it will be maximum. For instance, if I measure it here, my measurement will be again sinusoidal, but at a certain amplitude. When I go here, then it will reach its max value. But if I am right here, it'll basically be nothing. Okay? So there's this field where the wave's standing wave, meaning spatially nothing changes. It's just there. Spatially you have a minimum, maximum, another maximum, and so on. That's the difference between these two, standing wave versus propagating wave. It's like a long string. If you give it a pulse here, that pulse will travel. But if you have a reasonably short string, it will start coming back and forth, and you will have this shape that you see going up and down. Okay, so the difference between progressive and standing waves. Now, I want to talk about the concept of phase velocity, and we're going to see this over and over again today and later on in structures. Okay. We say ordinarily, here's an incident wave. Okay, and it has wave fronts. Let's see how I want to do this. Yeah. Okay. In time delta t, the wavefront moves at the speed of sound, a distance c times delta t. That's how the speed of sound makes it move, okay, in delta t. That's how the information is carried. But when you look at the wall, okay, the points, let's say this is the information that you're sending. This is a pulse, okay, A, B, in time. So A moves from here to here in that time frame. Now, that same change, again, C times delta t, the wall sees somewhat differently. Okay? You can see the spaces stretched, but it's much faster. Let's see why it is much faster. Theta I. Okay? And that theta I is the same as this one. Now we're talking about these two ratios, and the value of the distance between these would be C times delta t divided by sine theta I. You can see that it travels much faster. And this is called the phase speed. Sometimes it's called a trace velocity. The trace of the waves, oblique waves that are moving along. Okay. This is important, so why don't you write it down and let's just review it again very briefly. Okay. First of all, if you have any questions, please do ask now because this is important. We say wave is traveling at an oblique angle, okay, theta I, as before, against some sort of a wall. This could be a plate. This could be a window. This could be anything, or surface of a liquid, okay? And so plane wave is traveling. You can see if it's carrying a pulse like this, okay, that pulse is moving at a speed c. Okay, now these are the plane wave fronts, but what does happen is, whereas the distance between these is c times, let's say, a particular time period, delta t, the wall sees it a little bit different, and that is equal to c delta t over sine theta I, much longer. Okay, so for it to take to cover this distance in delta t, the speed is the speed is phase speed is c sine theta I, not the delta t. Okay, it has to travel faster to get to that point. Okay. That's the phase speed. Why is it important? Because depending on this angle, this distance changes, and these effectively determine the wavelength with which you're exciting another system. And I'll come back to it later. But in a moment, we're going to see refraction. Okay? That is sound is incident at a certain angle on one side, but it is at a completely different angle on the transmitted side. And these will become important at that point, okay, as far as how much sound is transmitted. Now, we just covered the rigid plane case. Okay, this is phase velocity. We looked at the rigid plane sound field in front of a rigid surface, and I think you probably can do the resilient boundary. How did we do that? And the condition here is, I think by now you're familiar with these. Okay. What is the boundary condition? Pressure is zero where? At x equals 0, pressure is equal to 0. And once again, that gives us a very similar result as before. And in this case, we can write the expression as 2I pi sine x. Always cosine theta. Okay. Once again, we have a standing wave, but in this case, the standing wave has pressure on the wall that's 0. Okay, whereas in this case, the pressure was a maximum. One more concept, that's the acoustic impedance of a surface. Reflecting medium. Okay. Here we represent the ratio of the reflected pressure to pi by a value r, coefficient of reflection. And from before, actually, I don't need to write these as separate. We now know that these have to be all the same angle. And the velocity on the surface so the acoustic impedance is the ratio if you let's see. Basically, that's the impedance expression. Okay, why don't you write and let me review them. Okay, so normalized impedance expression is zeta is equal to Z over rho C. What we're saying is that the impedance of the surface is represented by Z, but we normalize it with respect to what is rho C, the wave impedance or the specific acoustic impedance of the fluid, air, gas, etc. This is the normalized impedance. So rewriting this, just simplifying, where R is the ratio of the amplitude of reflected to incident waves. Okay. There are different ways of looking at this. One is you see the impedance here, normalized impedance. It's modified. It's actually made smaller by the angle of incidence, okay? Because this can never be more than 1, but it could go down to 0. What does this mean? This means, let me have your attention just for a second. This means you can almost make the impedance, not almost, theoretically, you can make the impedance of a surface 0 by changing the angle of incidence. That is when theta is pi over 2. And that means when the wave is propagating parallel to it, it has no impedance. It's as if there's no wall there. We'll get to it in just a few minutes in the next unit. Okay? But using these, let's find out what the ratio is in terms of the reflection ratio in terms of impedance. So let's see if that's correct. Yep. So this gives us the reflection coefficient in terms of normalized impedance and the angle of incidence. Okay? And you can write it, excuse me, in a number of different ways. For example, we know that zeta is z over rho c and cosine theta I is equal to kx over k. So you do a number of different ways to express this. Okay, one more thing before we finish this unit, and that is the notion of acoustic admittance. We did talk about this in the very first lecture, but now in this context we'll talk about the surface. So it is essentially 1 over the normalized impedance, 1 over zeta. Okay, and that means rho c. I put in parentheses omega because usually they are functions of the frequency, and usually they are complex quantities. So one would express it as a combination of real and imaginary parts, and we call the real part conductance, and we call the imaginary part susceptance. These are terms that you should know. Just for completeness, I'll write down the expression for impedance as well. That's the real part and imaginary part. Okay. So in these terms, we can express the conductance as coming from the real part, and susceptance is what would be the susceptance? Sorry, what would be the admittance for a rigid wall? Admittance for a rigid wall. You never heard of admittance? What's admittance? What's admittance? It's the inverse of impedance, okay? What's impedance? Physically, what does it mean? It's the resistance to motion. So when you're applying a force or a pressure, how much it resists. So admittance is just the opposite, how easy it is. So rigid wall has what kind of impedance? Pressure divided by particle velocity is impedance. What's the particle velocity on a rigid wall? Exactly. So what would be its impedance? Infinity. So what would be its admittance?
Zero.
Exactly. Do you agree? Yes, good. Okay. Well, that pretty much concludes this unit where we cover the oblique plane wave in one medium, okay? Just one medium where it is incident on a solid wall or it's incident on a pressure release boundary and so on. In the next unit, we'll cover what happens if the other side is another fluid, another medium, and where it penetrates, and we'll cover Snell's law. Okay, we'll take a couple of minutes of break.